nuclear energy. Fission and fusion. Nuclear fission. Principle. Nuclear fission is the process of splitting a heavy atomic nucleus, like uranium-235 or plutonium-239, into two smaller nuclei. This process releases a significant amount of energy, neutrons, and gamma rays. When a heavy nucleus absorbs a neutron, it becomes unstable and splits into two smaller nuclei. This splitting releases a large amount of energy in the form of kinetic energy of the fragments and electromagnetic radiation. Additionally, it releases more neutrons, which can induce fission in other nuclei, leading to a chain reaction. Nuclear fusion. Principle: nuclear fusion is the process of combining two light atomic nuclei, such as isotopes of hydrogen, like deuterium and tritium, to form a heavier nucleus. This process releases energy. Process fusion occurs under extremely high temperatures and pressures, similar to those found in the core of stars. In these conditions, the kinetic energy of the nuclei is sufficient to overcome their electrostatic repulsion. When the nuclei combine, they form a heavier nucleus and release energy in the form of radiation. Nuclear fuels are the heart of a nuclear reactor. Let's talk about some of the common nuclear fuels used today. First, we have uranium-235. It's a naturally occurring isotope of uranium, and it's used as fuel in most nuclear reactors. Next, there's plutonium-239. This one is a man-made isotope produced in breeder reactors from uranium-238. And finally, there's thorium-232. It's another naturally occurring element that can be used in reactors, particularly in a thorium fuel cycle. Now let's dive into the principles and types of nuclear reactors. So, what are the key principles of a nuclear reactor? First, we have the nuclear chain reaction. This is sustained by the controlled fission of nuclear fuel. Then there's heat generation. The energy released during fission is used to heat a coolant like water or gas. Next, we have heat exchange. The heated coolant transfers its thermal energy to a secondary system to produce steam. This steam then drives turbines connected to generators producing electricity. And lastly, control mechanisms are crucial. Control rods made of materials like boron or cadmium are inserted or withdrawn from the reactor core to control the rate of the fission reaction. Types of nuclear reactors. Pressurized Water Reactor, or PWR. The principle here is that it uses water as both the coolant and the moderator, keeping the water under high pressure to prevent it from boiling. The process involves a primary loop that heats the water, which then transfers heat to a secondary loop. This secondary loop produces steam that drives the turbine. Boiling Water Reactor, or BWR. The principle for this type is that it also uses water as both the coolant and the moderator, but it allows the water to boil directly in the reactor core. The process here is a bit different. Steam is produced directly in the reactor vessel and then sent to the turbines. Heavy Water Reactor, or HWR. The principle here is that it uses heavy water, also known as D2O, as both a moderator and a coolant. This unique feature allows the use of natural uranium as fuel. The process is quite similar to pressurized water reactors, but with heavy water effectively slowing down the neutrons. Fast breeder reactor, often abbreviated as FBR. The principle behind this type of reactor is the use of fast neutrons and a mixed oxide fuel, usually comprising uranium and plutonium. This combination generates more fissile material than it consumes. Interestingly, the process does not involve a moderator, and the coolant is often a liquid metal like sodium, which ensures efficient heat transfer. Gas-cooled reactor, or GCR. The principle here involves using a gas, typically carbon dioxide or helium, as the coolant, with graphite serving as the moderator. In terms of process, the gas circulates through the reactor core, absorbing the heat generated from fission, and then transfers this heat to a secondary system. Molten Salt Reactor, abbreviated as MSR. The principle of this reactor is quite fascinating, as it uses molten salt mixtures as both the fuel and the coolant. The process involves dissolving the fuel in the molten salt, which then circulates through the reactor core, transferring heat directly to a secondary system. Each type of reactor, including the MSR, has its own set of advantages and disadvantages in terms of efficiency, safety, fuel usage, and waste production. This diversity contributes significantly to the array of nuclear power generation technologies available today.